But if we have a closer look at this system, or these three equations, we see that they depend on higher order terms, in this case here on second order terms, and we would, for a full quantum description, we would also need to derive these equations to get the full dynamics of the system. But for some system, and especially for large open quantum systems, it is sometimes good enough to just approximate them, and the simplest approximation you could do is just to factorize these operator expectation, or this higher order operator expectation values, which in this case here would correspond just to the first order cumulant expansion. People call this also the mean field approximation. Of course, we could also keep these such second order terms, and then just approximate third order terms. This would correspond to a second order cumulant expansion, which I explain a little bit later. Yeah, so this would be the basic procedure of the cumulant expansion. If you do it by hand, you just derive the equations according to the commutation relations here, and then perform this cumulant expansion. Now, in the second step, I just briefly show you how we implement this in quantum cumulants.shell. So the first main thing we need to implement is this non-commutative operator algebra. Currently, we only have like two different Hilbert spaces implemented in quantum cumulants, one for harmonic oscillators and one for discrete energy levels. But it turns out that most Hamiltonians or most systems in quantum optics, but also in quantum information, can simply be reduced to combinations of these two Hilbert spaces, so there isn't much more than these two, actually. Yeah, for the implementation of the harmonic oscillator, we just need to somehow implement this commutation relation that the commutator of A and A dagger is equal to 1. And what we do to this end is just writing a rewriting rule that whenever we find the expression A times A dagger, we just replace it by A dagger A plus 1, which just corresponds to this rewriting rule. People also call this normal ordering for bosonic operators. Good, and for the discrete levels, we just assume, or we just use the orthogonality between different levels. This means if we have such a transition operator, if we have such a transition operator, we call this sigma, we get, if we multiply two transition operators of, for example, the same atom, we get either a new transition operator if these two indices are the same, so we have the Kronecker delta here, and if they are not the same, it's just basically 0, and yeah, we just end up with a 0. So that's basically the two different Hilbert spaces we implemented. Of course, we also want to deal with composite systems, so we want to build large systems with different subsystems, and to this end, we use the property that operators on different Hilbert spaces just commute, so we can always just order these operators according to the Hilbert space. This means we do not really need to think about it, we just order them on the Hilbert space on which it acts on non-trivially. Good. Within quantum cumulants, it looks like this. First of all, we always need to just specify which Hilbert spaces we want to have. In this case here, we have one Fock space, for example, for a cavity mode, and we have one n-level space here for a two-level atom, so this means a two-level space here. The full Hilbert space is then, of course, just the tensor product of these two Hilbert spaces, and on this full Hilbert space, we can then define our operators. We define here the destroy operator with the name A, and it's acting non-trivially on the first Hilbert space. This means on the Fock space. For the transition operator here, we define the transition from I to J, or actually from J to I, with the symbol sigma here, and it's acting non-trivially on the second Hilbert space. Yeah, and if you use now these two operators, we find that we multiply, or not we find, we implemented it like this. If we multiply A times A dagger, we find that it's A dagger A plus 1. If we multiply two transition operators, we find that it's either a new transition operator if these two indices are the same, or we get 0 if these two indices are not the same, just due to the orthogonality between different states. Yeah, and if we have a product of different operators, we just find that we can order them according to the Hilbert space. Good, so that's the implementation of this non-commutative algebra. The other main thing we need to implement is the cumulant expansion. What you saw in this brief example at the beginning was the very basic or the simplest cumulant expansion to first order, so the mean field approximation, but of course we can also do higher order approximations. And the main or the crucial element in all of this cumulant expansion is the so-called joint cumulant. It's written up here. This is the joint or the general expression for a joint cumulant of nth order. It's pretty hard to understand this in like 1 second, therefore I will just show 2 explicit examples. The joint cumulant of second order, this means for 2 operators, is simply the difference between the average of the operator product minus the product of the 2 averages. And for a third order term, it's basically more or less the same. It's just the average of the third order product minus lower order ones. So we end up with a very similar expression, even though it gets much more complicated the higher the order is. Yeah, and this joint cumulant is basically just a measure for how much quantum correlations are in a set of operators. Good. Yeah, with this definition now, we could in principle just calculate this joint cumulant for different operators in our system. And if they are 0, we know that there are no quantum correlations between these operators. For the cumulant expansion, we just basically reverse this statement. We just assume that some correlations are 0, and then we get these rewriting rules or these approximation rules that if we want to do, for example, a first order cumulant expansion, we need to replace these second order terms by the product of the 2 averages. If we want to do a second order approximation, we need to replace third order operator products or average, a third order average, by this expression here. And the first order would correspond to the mean field approximation, as I said before. The second order approximation is, for example, exact for Gaussian states. So this sometime, or most of the time, this works really well for large open quantum systems. Okay, and again, within quantum cumulants, we have here the very same operators as before. We can just calculate this joint cumulant in the first line here, where you see that the joint cumulant of this A times sigma 2 is just the product of the operators, or the average of the product of the operators minus the product of the 2 averages. And if we calculate now the cumulant expansion to first order, we see that it's just the product of the 2 averages. For a third order term, we can, for example, calculate the second order cumulant expansion, and what we obtain is this more or less complicated expression here, just for the second order cumulant expansion of this third order term. Okay, good. That was basically the implementation. So we have this non-commutative algebra, and we have the cumulant expansion. Now in the third part, or in the last part, I want to show you a few examples, which you can either find in our paper, or it's also on our documentation of quantum cumulants if you want to have a look. The first example I want to show here is on optomechanical cooling. The basics of optomechanical cooling: you have 2 mirrors. There's light inside the mirrors, and the light inside the mirrors just cool one of the cavity mirrors. It doesn't really matter now what the physics is exactly. It's just important that we can describe such a system with this Hamiltonian here, and it has a decay channel of the cavity photons, which is described by a jump operator A, and the corresponding rate kappa. Yeah, again, the first step we need to do in quantum cumulants is to define the Hilbert spaces. In this case, it's 1 Fock space for the cavity photons, and it's 1 Fock space for the cavity phonons, which describe the motion of the cavity. Full Hilbert space, of course, is again the tensor product of the 2 Hilbert spaces, and on this full Hilbert space, we can now define our operators, which are 2 destroy operators, 1 for the cavity photons and 1 for the cavity phonons. Yeah, and with these operators, we can, or after these operators, we can then just define symbolic parameters. And with these operators and symbolic parameters, we can just basically define our Hamiltonian and our dissipative processes just according to the description what we have above here. So we have just the same Hamiltonian and same jump operators and rates as above here. Good. yeah, having this Hamiltonian, jump operators, and rates, we can simply use the mean field function in quantum cumulants, which derives the mean field equations for a set of operators, in this case here, A dagger A and B dagger B, which correspond to the photon number and to the phonon number, just for our Hamiltonian, jump operators, and rates. And we want to do it here up to second order. What we get are these two equations here, which are, as you see, not really complete, because we have, on the right-hand side of the equation, we have expectation values as, for example, this A dagger, which doesn't appear on the left-hand side of the equation. So to be solvable, the system needs to be, or differential equation system needs to be complete in itself. This means we also need to get the equation for these operator expectation value. To do so, we just need to call the complete function in quantum cumulants, which completes now our set of equations, and we get these 8 equations here, which now completely describe our system of this our optomechanical system within a second order cumulant expansion. Good. Yeah, with this, actually, we are more or less done. The only thing we need to do is defining an initial state, defining some numerical parameters of a realistic system, and then just solve it numerically with, for example, differential equations.gl. And what we get is, in this case here, cooling of the cavity mirrors up to some whatever millikelvin or so. And yeah, it's done by the cavity photons, or the photons inside the cavity. Good. That was the optomechanical cooling example. Sorry, wrong thing. The next example I want to briefly mention here is on the super radiant laser, which was basically the example we needed the package for at the very beginning. It's more or less the same example as you saw at the very beginning of the single atom laser. The main difference, or actually the only difference, is that we have many atoms instead of only one atom. Again, very beginning, we need to define the Hilbert space, in this case here, one Fock space for the cavity photons and one n-level space for the two-level atoms. On this full Hilbert space, then, we can just define again our operators. And the special thing here is that we do not only have a normal transition operator, but we have a transition operator with an index, which we can define by this indexed operator. So we have really operators which carry an index I. Good. Yeah, with then defining, again, symbolic parameters where we can also have index variables, we can then just simply define our Hamiltonian and, again, jump operators and rates, and use it in the mean field function to get, again, the set of equations which describe our system. Yeah, what we want to do here is, again, complete the set of equations because we want to solve it numerically. But since we are smart physicists, we know that some of these expectation values are always 0 within the system, just due to the phase invariance of the system, because we drive it or we bump it incoherently, so there's never a phase inside this system. So terms which would carry a phase are simply 0. If we know this, we can just give a keyword to the complete function that it should just neglect these phase invariant terms with a filter function. And doing so, we just end up with these 4 equations, which basically completely describe now our system in second order. Yeah. There's another nice feature what we can use now. If we assume that all atoms are just identical in this system, we know that all these operator averages for different atoms just do basically exactly the same thing if they just start in the same thing. This means we do not really need to derive all the equations for all the different atoms. We just know that all atoms basically do the same. This means we can scale up our system, which replaces all these different sums by only a factor of n, and we only end up with these 4 equations, which means it's super practical to describe very large systems because the atom number just enters as a numerical factor, so it doesn't grow with the, so the system itself, the number of equations doesn't grow with the atom number, and it's pretty cool actually. We can really describe systems with millions of atoms, which you could never do with a full quantum description, or also with other approximations, usually not. Okay, yeah, then we are more or less done again. Just define the initial state and some numerical parameters, and we see the time evolution of this system. Okay, and then just to briefly come back to the example at the very beginning where I showed these like 2 pages of equations. This is the program which derives them. The main thing I want to emphasize here is that it's not much different as the superradiant laser example. We just have one additional Hilbert space. We can't use this phase invariance because we drive our system coherently, or we drive the atoms coherently. But this then leads already to whatever these are, like 20, 25 equations or so, which, okay, I mean, you could derive them by hand, but I think you shouldn't, because you will probably get some error somewhere, and then physics is not correct anymore. Yeah, and that's basically what I wanted to show on the side of the examples. Let me briefly sum up what I showed you in this presentation. So at the very beginning, I showed the implementation, which basically reduces to implementing the operator algebra and the cumulant expansion. Then I showed some practical examples on the optomechanical cooling and on the superradiant lasing. And let me just briefly mention some features which weren't shown in this in the examples I showed before. We can, for example, also derive the equations for 2-time correlations functions, which allows us also to calculate the spectrum, which is, for example, relevant for the superradiant laser. We can also do time-dependent functions, or time-dependent systems, where we define time-dependent Hamiltonians or time-dependent decay rates. And it's also not too difficult to define your own operator algebra or your own custom operators with our Q-number interface. So it's actually not too hard. So you could, for example, implement position and momentum basis. Yeah, and things we are working on now is to make an interface between our other toolbox, quantumoptics.gl, and quantum cumulants, basically to define the initial state, because sometimes this is quite annoying because you need to find all the right expectation values, and it's not always too easy. And another thing is what some people are interested to include measurement back action, which basically just enters as an additional stochastic term in the equations. Okay, yeah, if you're interested, we have a paper on it. We have, of course, a GitHub repo and a documentation, and there's also a master thesis on the symbolic summations. Yeah, and all of this has been started and mainly implemented by David Blankensteiner with a little bit of help from my side, and I extended it with some new features. The symbolic indexing and the symbolic summations has been implemented by Julia Moser in his master thesis, which was, let's say, co-supervised by myself, and everything was supervised by Helmut Rich. Thank you, and I'm happy to answer some questions.
Yeah, thanks very much. And of course, the floor is open for question, and the first is up here.
So I find you have like these nice calculations for two-time correlations. Do you have any plans for like higher order, like 3-time or n-time correlation?
I mean, you can do. Yeah, the 2-time correlation. No, okay. Correlation-wise, on time we can just do it on 2-time. Yeah, there's not more implemented, but this is enough to calculate the spectrum, and yeah, no, but it's only possible to do two-time correlation functions, but not like higher order.
I see. Like, for example, do you have plans for like quantum regression of them? This kind of calculation for higher order higher order correlations.
I mean, you mean with respect to these time correlation functions?
Yes.
No, in this respect, not. So we do not really have a need for this at the moment, but maybe in future it might be relevant.
So could you also take only partly the expectation value in order to, for instance, get an effective Hamiltonian which is significantly simpler than the full Hamiltonian? So there's this method for Cooper pairing where you're interested in the pairing mechanism where you introduce another field and then you
I guess what you want is like expressing some parts of the Hamiltonian in a mean field or a second order approximation and keeping the other one in a full quantum description or something like this. Right?
Yeah, there's this weird approximation where you have like a four-body operator, and then you want to reduce it in terms of two-body terms.
Yeah.
And you only take partly the expectation value.
I mean, it's not working out of the box, but I think you could play around a little bit and find. So what we can do is doing some mixed order, for example, that we don't keep like only second order terms, but keep like correlations between some particles to higher orders and between other particles to some other order. So this works, but like in general, it's not like implemented that it works out of the box now. Yeah.
I mean, this could be used for some kind of functional renormalization where you don't know what is the effective Hamiltonian, but you generate a basis of all the terms which might be relevant, and then you just use differential equations to let it flow to some effective parameters, so to say. But you still keep an operator. You don't want to take the expectation value of the full operator. Anyways, yeah.
Yeah, we can discuss it later. I need to think about it a little bit more. Yeah.
We have time for one more quick question. All right, then in that case, up.
Yeah.
Yep.
To what extent is this, you mentioned using the operators, do you have a clean sort of API interface, more or less, between the cumulants and the operators, the rules for the space, I should say?
Okay, you mean for XMP basis, for example, or for position momentum basis?
Yeah, for instance, for those.
Yeah.
So you have two different kinds of spaces. I mean, you could even use this for probabilities, because I think the formula is the same as probability cumulants.
Yeah, it's the same. This is just the extension to operators.
So if it's generic enough that you know, people could
I
use
mean,
this.
what I wanted to say with this Q number interface is that one just can define some operators rules or rewriting rules, and it's super easy within quantum cumulants. And then you can just use these operators, and it will just replace.
All right, so it's already set up for that.
Yeah, exactly.
Some new rewriting rules for another space,
Yeah.
and I can tensor it and everything.
Exactly. Yeah.
Right?
Yes.
Yeah, that's good. Thanks.
All right, thanks very much. Let's thank the speaker again. And yes. Yes, it's your turn. Yeah, next is Stefan Krasnov on formalism acoustic quantum hardware simulations.
Testing. Okay, so